Hello guys, welcome to our fifth lecture on photonic devices. On today's lecture, we're going to talk about the parabolic approximation of the band structure and also the density of states as well as the wave vector values in K space. So let's start by recapping a few concepts from our previous lecture. The density of states, rho of E, allows us to calculate the number of states in a range of E values. So we mentioned that if you have a band structure, graph of E versus K, you can have a distribution of states which is not uniform. So you might have, for example, less states close to the band edge, right? The band edge. And or a smaller density of states and a larger number of states as you go up in the band. So you have a larger density of states up here than you have down here. Down here they are more spaced apart, whereas up here they're more close together. So you have a larger density of states, for example, up here as compared to down here. Okay, so this is the density of states, the number of states that you have as a function of E, the density of states. So this is a quantity that is expressed as a quantity per unit volume. So it's the number of states per centimeter cubed. Okay, so you usually express it as in centimeter to the power of -3 for that reason. Okay, so if you take a piece of a small cube of semiconductor with a side of 1 centimeter, rho is going to be the density of states per unit volume, or in this case, per cubic centimeter. But what is a state? Okay, a state, which can also be called a mode if you think of Schrodinger's equation as a wave equation. So you have spatial modes, just like in optics you have spatial modes. A state is an allowed solution to the boundary value problem. In our case, the periodic potential distribution is inside a bounded region of space. So the state is associated with probability density function. The probability of finding one electron is given by this, okay, mod psi squared, and also the state is associated with a quantized or discrete energy value. So each state will be associated with the corresponding probability density function or the wave function and its discrete energy values. Okay, so if we recall that we mentioned that, for example, for the hydrogen atom, you have the density clouds around the nuclei that had some distribution in space and so on and so forth. So this would be the probability density functions or the wave functions. And to each wave function, you have associated with it a discrete energy value. So this state would have one given E, this other state would have another discrete E value. Well, the same thing happens for a solid. The difference is that in a solid, instead of only one atom, you have a collection of atoms packed close together in space. But in this region, let's say this region where you have the solid, you also have a probability density function, which is not going to be exactly this, but will be a distribution inside the solid in three-dimensional space. And for each state, you have a different, wave function and the corresponding quantized energies of the corresponding wave of the corresponding electrons. So if you look at the band structure, remember that we only need to look at, for our purposes, to the regions close to the band edges for the conduction band and the valence band. Of course, these bands would have a more complex structure as you got away from the band edge, but we only need to look at this region for the purpose of modeling and developing optoelectronic devices. Well, in this picture, the black dots here uh, are meant to illustrate the states. Okay, they're not necessarily occupied by electrons, but they are states that electrons could occupy, possibly. Um, Also, I mean, this is of course not up to scale. You would have much more states than are illustrated here. This is only for illustrative purpose. So there is a one-to-one correspondence between the k values and the energy values, the wave vector values and the energy values in the band structure. So as we plot the energy and k values in the band structure, you will notice that there is a one-to-one correspondence in the sense that this, this point in the graph is going to be associated with one state which has a probability density function that has this energy and this wave vector value. So there's a one-to-one correspondence. Okay, this is the wave vector value and the energy of the corresponding state. So there's this one-to-one correspondence. So we should also recall that the density of states rho of k is defined so that rho of k dk is the number of states available between k and k plus dk per unit volume. So just as we defined rho of E, right? The density of states expressed as a function of E, here we were talking about rho as a function of k, but rho of E is defined so that rho as a function of E dE is the number of available states between energy values E and E plus dE per unit volume. Okay, so you can define a density of states as a function of wave vector k or as a function of energy E in similar manners. Going back to the picture, rho of E at this point here would be the total number of states between this energy value and E plus dE, so the states within this region, as of course dE became infinitesimally small. So this is a differential energy, right? In this limit, we said that rho of E is, for electrons in the conduction band, the derivative of the electron carrier concentration with respect to energy. Okay, this is a consequence of what we just said, if you think about it. And, well, you can make these same definitions expressing the density of states, rho, as a function of k. Okay, so the difference is it's only the dependent variable, but it's closely related. So the density of states rho as a function of k is the number of states with wave vectors, absolute value of course, between k and k plus dk. And since there is one-to-one correspondence between k and e, for each state you'll have the k and the respective e plotted in the band structure, we must have rho of E dE equal to rho of k dk. So if this is the state, this is the total number of states with energies between E and E plus dE, and this is the total number of states with k values between k and k plus dk, we see that these are the same states. Okay, you have the same number of states. Of course, if this E corresponds to this k, then the number of states between k and k plus dk are all of these states right here, which are the same number of states, or the same states with energies between E and E plus dE. That's why we can say that this equality holds. So this only means that the number of states between k and k plus dk is the same number of states with energies between E and E plus dE. Okay. For semiconductors, we saw that the valence band is completely filled at 0 Kelvin. At 0 Kelvin, if we plot the band diagram, the conduction band would be completely empty, and the valence band in a semiconductor would be completely filled with electrons. You would neither have holes in the valence band nor electrons in the conduction band, and this is at 0 degrees Kelvin. Another important information that we saw in the first few lectures of this course is that the number of electrons in the valence band is of the order of 10 to the 23rd, 10 to the 24th electrons per centimeter cubed. At room temperature, so if you raise the temperature from 0 K up to 300 K, around 300 K, a few electrons acquire enough energy to move to the conduction band. So, for example, in silicon, the carrier concentration at room temperature is 10 to the 10th electrons per centimeter cubed. Okay, so as opposed to 0 electrons at 0 K, if you raise the temperature to 300 K, you will now have, I will depict this in a different manner, but you now have a few electrons here at close to the edge of the conduction band, and because these electrons moved up in energy to the conduction band, they're going to leave behind holes, which I'm going to draw like this. But so these electrons, when they move up, they leave behind a few holes, which are these empty circles in the valence band. Okay, and for silicon, this is of this order, 10 to the 10th per centimeter cubed. For a doped semiconductor, you can get much larger values. So the number of carriers in the conduction band, electrons, and carriers in the valence band, holes, is of the order of 10 to the 12th up to 10 to the 17th, or even larger, 10 to the 21st, and so on, per centimeter cubed. So by doping the semiconductors, you can introduce electrons in the conduction band and holes in the valence band, and raise this number up to much larger values. In fact, even larger than these ones right here. So these numbers are much, much smaller than the total number of states in the conduction band or the valence band. So if you take even 10 to the 20, 10 to the 17 or 10 to the 20 is much smaller than 10 to the 23, 10 to the 24. So orders of magnitude smaller. And that is why only the states at the edge of the conduction band are occupied, because you have lots and lots of states. Let's take a look at the band structure again. You have lots and lots of states in the conduction band and in the valence band, and you should remember that only electrons that have enough energy to transit from the valence band into the conduction band can make this transition. So it's more likely for the electrons that are close to the band edge, the valence band edge and the conduction band edge, to make the transition, and therefore the states that are more likely to be occupied are the ones close to the band edge. Well, if you have 10 to the 17 electrons for a doped material, much less for an intrinsic material, 10 to the 10th or something like that. This is a small fraction of the 10 to the 23 states that you have in the entire band. So that means that only the states at the very edge will be occupied, and the electron tends to stay at the lowest energy available always. So these states will be filled. Therefore, for this reason, we need to remind ourselves that to analyze the optical and electronic characteristics of semiconductors, it's sufficient to know the EK characteristics or the band structure at the edge of the respective band. So at the bottom of the conduction band, like this, and it's only important to know about the holes that are at the top of the valence band. So we're only interested in these regions, and at these regions, the edges, the band edges, the function that describes E as a function of k is to a very good approximation a parabola. So this brings up the parabolic approximation, an important approximation. For most intents and purposes, it's sufficient to consider that the band close to the edge is approximately a parabola, both the valence band and the conduction band. Therefore, the energy of an electron in the conduction band is approximated by this equation, which is the equation for a parabola if you take the x-axis to be k and the y-axis to be E, as we do when we're plotting the band structure. So this describes a parabolic equation. EC is the energy at the bottom of the band, and M star is the effective mass, in this case for the electron. So this would describe the conduction band for E larger than the band edge. And if we draw this, we can consider that we might have originally a band structure for the conduction band which might be more complex. Let's say something more complex. Okay, and of course this here is EC, the energy at the band edge. But by doing the parabolic approximation and by using this equation, we approximate the energy close to the band edge by a parabola. And if you're very close to the band edge, this parabola should approximate very well the energy band. Okay. Therefore, that's all we're doing here. In fact, when we define the effective mass, m star was equal to 1 over h bar squared multiplied by the second order derivative of the energy as a function of k, right? So if you substitute this energy here, you will see that what will result will be this value here, okay? So the effective mass of the electron, we can see it, is defined based on the parabolic approximation, okay? If you can do this, if you take this quantity and substitute here and calculate, you will get m star. Okay, so this is the parabolic approximation for the conduction band. Well, if an electron moves to the conduction band from the valence band, which is down here somewhere, it will leave behind an empty state, which, as we saw, is a hole, which can behave as a carrier and conduct electricity and so on. So for an intrinsic material, you will have a number of the order of 10 to the 10th holes per centimeter cube, because 10 to the 10th electrons have moved up to the conduction band. So we need to be concerned with the valence band as well. So you have a similar equation for the valence band. This is the band edge energy for the valence band, EV right here. mh star is the effective mass for the holes. And well, if we draw the band structure for the valence band, E as a function of k, as we said, you might have something more interesting describing the actual band, but when you do the approximation, you're taking the energies close to the band edge to be close to this parabola right here, which is in fact a very good approximation. It might not seem so in my drawing, but this is actually a very good approximation, considering that the states that we are concerned with here, both in the conduction band and the valence band, are states that are close to the very edge of the band, so mostly this region. So parabolic approximation is a very good approximation here. EV, of course, is the band, the superior limit here, the band edge for the valence band. And notice, of course, the minus sign here, which, you know, is related to the fact that this is an upside down parabola. It's turned upside down. But that's it. You can approximate, and the same comments that we've made regarding the effective mass apply as well here. Okay, the definition of the effective mass comes from the parabolic approximation. In fact, you can. A very good question is how, if a hole is the absence of an electron in a chemical bond, how can it have a mass? Okay, so this mass is related to the acceleration that the hole will have, or the movement, the velocity that the hole will gain in the lattice, and it's only a quantity which is defined for these purposes. It's not the actual mass of a hole, because a hole is the absence of an electron. So in practice, it should not literally have a mass. It is only defined for this purpose. Another observation is that although these equations represent continuous curves, okay, this equation right here and this equation right here represents a continuous curve of E in function of K, energy in function of wave vector. The actual curves correspond to discrete points. Okay, so instead of having this continuous curve, what you actually do have are discrete points in this point. So we should not be confused from the fact that these are continuous curves, and always remind ourselves that what you do have is discrete points along these curves. Okay. Finally, this table summarizes some important data regarding some semiconductors. Okay, these are organized in terms of band gaps. So the rows closer to the top have wider band gaps, and as you go down, the band gap gets smaller. Okay, so for gallium nitride is a wide band gap semiconductor. You have 3.4 EV, and then as you go down, as we said, gallium arsenide has 1.424, indium phosphide 1.34, silicon 1.12, and germanium 0.67 electron volts. Okay, this column right here shows us which ones are direct and which ones are indirect band gap semiconductors. Basically, silicon and germanium are indirect band gap semiconductors. And here you see the effective mass for electrons and holes, okay, which for the parabolic approximation is very important. And these are expressed as a function of the actual mass of the electron, the mass that the electrons actually do have, which is 9.1 times 10 to the minus 31 kilograms. Okay, so you see that you have a fraction of the mass. Okay, so for example, in gallium nitride, the effective mass of the electron is 20% of the actual mass of a real electron, and the mass of the hole is 80% of the actual electron mass. Okay, for silicon here, you see that the electron has almost 100% of the electron mass, and the hole has about one half of the electron mass.